Welcome to an extraordinary journey through the hidden world of engineering. Tonight, you'll discover astonishing facts about the inventions, principles, and innovations that shape everything around you, from towering skyscrapers and massive bridges to tiny circuits inside your phone. Before we journey further, feel free to leave a comment with from what location you're watching this and what time it is there. Now settle in as our exploration truly begins. Engineering surrounds us in ways subtle and spectacular. It is the silent architect of modern life, the invisible force turning imagination into reality. Have you ever wondered how a single steel cable supports a suspension bridge, holding thousands of tons while swaying gently in the wind? Or how microscopic transistors packed billions deep inside your smartphone process information faster than the human brain? Each of these wonders begins with principles, laws of physics, material behaviors, ingenious designs that engineers harness with incredible precision. Consider the foundation of a skyscraper sunk deep into the earth. It must bear immense weight and resist earthquakes forces millions of years in the making. Civil engineers design these foundations using models that account for soil variability, moisture content, and compaction over time, ensuring safety without visible signs of stress. Shift your attention to mechanical engineering, where gears and levers manipulate forces with finesse. The gear train in a watch, for example, is a universe in miniature. Each tooth is painstakingly designed to minimize friction and wear, enabling timekeeping over decades without interruption. The precision is so exact, the tolerance sometimes mere microns thinner than a human hair. Electrical engineering electrifies our world not just through power generation but through the dance of electrons in circuits. Transistors, the building blocks of modern electronics, function by controlling electrical current flow in silicon layers no thicker than a sheet of paper. The science and craftsmanship behind these tiny switches underpin everything from space exploration to streaming your favorite show. Venture into chemical engineering and glimpse how raw natural resources transform into fuels, plastics, and medicines. The intricate balance between reaction rates, temperature, pressure, and catalysts is fine-tuned to maximize yield and minimize waste, often through processes that must be safe on massive industrial scales. Each discipline adds a unique thread to the vast tapestry of engineering, yet they all wrestle with shared challenges: uncertainty in materials, unpredictable environments, human factors, and the limitations of knowledge itself. As you listen, let your mind drift into the layers beneath everyday objects and systems. Romance the idea that each design carries countless unseen hours of research, testing, and adjustment, and that beneath the surface of familiar things lie stories of triumph over complexity and constraints. Tonight's journey will ebb and flow, revealing, hinting, and inviting curiosity, without rushing toward easy answers. It is a slow, immersive voyage across fascinating facts and deep reflections, perfect for easing your thoughts and welcoming rest. And remember, this is only the beginning. Much lies ahead, waiting to unfold with quiet wonder. Now that we have set foot on this vast journey, let us turn our gaze toward the silent giants that shape our world's skyline. The foundations and frameworks of civil engineering. Imagine a massive skyscraper piercing the clouds, a feat only possible through decades of knowledge about Earth, materials, and design. Before the gleaming glass and steel surfaces arise, the true hero emerges beneath the surface, the deep foundation. Foundations serve as the unseen anchors holding towering structures steady against gravity, wind, and even the trembling of earthquakes. The engineering gamble is profound. These bases must transfer immense loads through layers of soil and rock, materials themselves alive with variability and unpredictability. Soil is not just dirt, it possesses unique properties that shift with moisture, density, and compaction history. Engineers study these nuances through field tests and laboratory analysis, modeling subsurface behavior to predict how the ground will respond under pressure. Designing optimal foundations requires balancing strength, cost, and environmental impact. Pile foundations, for instance, involve driving long, slender columns deep into the earth to reach more stable substrata. But every pile's length, diameter, and spacing is calculated meticulously. Too few or too thin, and the risk of failure rises. Too many or oversized, and budgets soar unnecessarily. Engineers even must account for long-term soil consolidation, the gradual settling and compression of soil layers that can subtly shift the structure over decades. But foundations form only one piece of the puzzle. The superstructure, the visible frame of beams, columns, and floors, must marry architectural vision with mechanical resilience. Steel, with its incredible strength-to-weight ratio and ductility, often serves as the skeleton of these giants. Yet steel itself is complex. Microscopic imperfections, weld quality, corrosion resistance, and temperature effects all dictate how well the material performs. Engineers apply sophisticated design codes integrating decades of research and real-world failure analysis to set safety margins. Even the arrangement of beams and braces responds to careful scrutiny. Triangular trusses distribute loads efficiently, but require precise assembly to avoid twisting and buckling. Moment frames provide flexibility during earthquakes, but demand rigorous detailing and connection quality. Every joint and bolt is engineered for reliability, recognizing that a small failure magnifies exponentially under stress. The interplay of these elements transforms simple raw materials into poised, safe, and functional marvels. Think, too, of how engineers model wind action on high-rises, employing wind tunnels and complex simulations to understand vortex shedding and aeroelastic effects. These invisible forces cause periodic swaying that occupants might feel or damage components if not managed properly. Tuned mass dampers, massive pendulums or fluid systems installed high in buildings act quietly to absorb these oscillations, an elegant blend of physics and engineering. Yet, beyond concrete and steel, modern civil engineering embraces sustainability, minimizing carbon footprints through alternative materials like engineered timber or recycled concrete, integrating green spaces, and designing for energy efficiency all reflect a growing consciousness of broader impacts. Climate resilience, preparing infrastructure for floods, heat waves, and storm surges, adds yet another technical dimension layered with social responsibility. Tonight's facts are only droplets in this vast ocean of complexity, but each droplet holds a story of human ingenuity confronting nature's unpredictability. Feel that slow awakening in your mind as these layers accumulate, building a mosaic more intricate than surface appearances reveal. Step closer to the heart of engineering's tangible essence, the materials that make invention possible. Steel, concrete, aluminum, polymers, composites, all have unique stories written in their atomic arrangements, thermal behaviors, and mechanical challenges. Understanding these materials is to unlock the secret language of strength, flexibility, and durability that supports every human creation. Steel, perhaps the most celebrated material in modern engineering, owes its strength to the delicate dance of carbon atoms within iron's crystalline lattice. Minute shifts in carbon content, from fractions of a percent to levels pushing hardness, completely alter steel's characteristics. Engineers harness these variations precisely, choosing grades tailored to specific structural demands, whether it's a skyscraper's framework or the thin sheet metal in a car's body. But raw strength is not everything. Steel's behavior under repeated stress, fatigue, is one of engineering's most studied phenomena. Imagine a metal cable endlessly vibrating under wind or traffic loads. Over time, tiny cracks initiate microscopically, then grow invisibly, silently threatening failure. Predicting fatigue life involves experimental data, fractography, and complex modeling, enabling engineers to design structures that endure for decades, even centuries, under dynamic forces. Concrete, often overlooked, is a marvel of chemical and physical complexity. Unlike steel, concrete's strength evolves slowly through curing, a chemical reaction where water and cement transform aggregates into a stone-like matrix. Porosity, moisture content, temperature during curing, and mix composition all drastically influence the final strength. Engineers must account for shrinkage, cracking due to thermal gradients, and long-term creep, where concrete deforms slowly under constant load. Innovations like fiber-reinforced and ultra-high performance concretes push boundaries in strength, ductility, and durability. Then there are lightweight alloys like aluminum and titanium, prized in aerospace and automotive design for their high strength-to-weight ratios. These metals challenge engineers with issues like corrosion resistance, weldability, and cost. Aluminum's oxide layer protects against rust but requires special surface treatments for paint adherence or bonding. Titanium, while exceptionally strong and lightweight, presents difficulties in machining and joining, demanding specialized processes. Polymers and composite materials blur traditional boundaries. Carbon fiber reinforced polymers, for example, combine strength, lightness, and flexibility, but work through complex anisotropic behavior. Strength varies with direction, demanding careful layup design and testing. These materials open new frontiers but require sophisticated failure analysis, damage detection, and manufacturing control to ensure reliability. Temperature effects reveal another layer of material complexity. Expansion and contraction with thermal cycling can induce stresses leading to cracking or warping. Engineers design expansion joints in bridges and pipelines to accommodate these movements. Safeguarding integrity. Extreme environments, cryogenics or high heat, push material limits further, requiring exotic alloys or ceramics. Advanced characterization techniques. Electron microscopy, X-ray diffraction, spectroscopy allow engineers to glimpse atoms and grain boundaries, diagnosing flaws or tailoring treatments. These microscopic understandings inform macroscopic choices that translate into safe, resilient structures and devices. Material selection is never arbitrary. Each choice is a delicate negotiation among mechanical properties, cost, availability, manufacturability, environmental impact, and lifespan requirements. Sustainability now drives innovation toward biodegradable polymers, recycled metals, and low-carbon concrete variants. Tonight, as these facts weave through your mind, consider that every material you encounter is a triumph of science and ingenuity, forged through relentless experimentation and innovation. In the grand architecture of engineering, materials form the canvas, the substance reality paints upon. Forces those invisible hands molding the world are the true challenges engineers must master. To build a bridge, construct a jet engine, or craft a smartphone, one must understand how materials respond to stress, strain, and energy flow. Mechanics. The science of these interactions is the foundation of every engineering feat. Imagine the complexity behind a simple beam supporting weight. Not only does it bear static loads, but it also must resist bending, twisting, and vibrations. Each force generates internal stresses distributed unevenly along its length and cross-section. Understanding this requires defining stress tensors, strain relationships, and elastic limits, concepts developed through rigorous experimentation and mathematical modeling. Beyond static loads, dynamic forces add layers of complexity. Vehicles crossing a bridge introduce shifting loads. Wind gusts create oscillations. Engineers use modal analysis to predict natural frequencies and avoid resonances that can amplify vibrations catastrophically. as devastatingly illustrated by historic bridge failures. Material behavior under load is far from uniform. Some materials yield gradually, others fracture without warning. Plastic deformation, fatigue, creep, and fracture mechanics form a vast lexicon describing how materials fail and how engineers prevent such failures. Fracture mechanics, for instance, investigates crack initiation and growth, illuminating how microscopic flaws can propagate into catastrophic breaks. Fluid mechanics governs how liquids and gases move around and through structures, essential not just for water treatment plants but for aerospace and automotive design. Turbulence, boundary layers, lift, and drag demands precise modeling and testing, often via computational fluid dynamics (CFD). Yet simulation alone is never enough. Wind tunnels and physical testing validate these models. Thermal stresses complicate matters further. Temperature gradients induce expansions or contractions that strain components, sometimes fatally. Engineers often design with thermal management in mind, using heat sinks, insulation, or active cooling systems to protect sensitive electronics or maintain structural integrity. Control of forces extends into the realm of vibrations and acoustics. Noise reduction in vehicles or buildings means understanding wave propagation, resonance, and energy dissipation. Active vibration control using sensors and actuators represents the cutting edge, merging mechanical and electrical engineering. Statics and dynamics drift into biomechanics when engineering intersects with the human body. Prosthetics, medical devices, and ergonomics all apply force analysis, tuned for biological tissues, nonlinear, and anistropic behaviors. Today, nonlinear mechanics pushes boundaries, analyzing large deformations, instabilities, and chaotic behaviors that classical linear theories cannot capture. This requires advanced math, numerical methods, and high-performance computing. In all these realms, engineers meticulously map forces, predict outcomes, and design safety factors to prevent failure despite uncertainty. Each calculation, each test, strengthens the delicate trust between human ambition and the laws of nature. Innovation, the lifeblood of engineering's endless progress, is where creativity meets precision to birth something new. The challenge is profound, to conceive solutions unimagined, to bend constraints into opportunities, and to balance risks with rewards in pursuit of improvement. History brims with examples where imagination unraveled seemingly impossible problems. The invention of the steam engine sparked a revolution, a clever harnessing of thermodynamics and mechanics that powered industries. Slight shifts in design, fueled by iteration and insight, transformed mere concepts into machinery that reshaped societies. Inventive engineering requires more than knowledge. It demands perspective, a way to view problems from multiple angles. Sometimes breakthroughs arise from cross-pollination, where principles from one domain unlock mysteries in another. Biomimicry, for instance, taps nature's designs like the aerodynamic form of the kingfisher inspiring bullet train noses to reduce noise and energy consumption. The spark of innovation often ignites amidst constraints, tight budgets, limited materials, or extreme environments. Within boundaries, creativity finds freedom. Engineers improvise with alternate materials, novel geometries, or unconventional processes. The Apollo missions, built in tension against geopolitical urgency and technical limits, exemplify daring innovation layered with relentless refinement. Process innovation also drives engineering progress. Additive manufacturing revolutionizes prototyping and production by building complex geometries, layer by layer, enabling custom parts impossible with traditional machining. Automation and AI introduce paradigm shifts in design optimization and quality control. Yet innovation demands patience. Ideas undergo cycles of failure, analysis, and improvement. Failures are valuable teachers, revealing unforeseen flaws or new paths. Engineers cultivate resilience, learning from setbacks, adapting designs, and persevering toward success. The role of collaboration and creativity cannot be overstated. Diverse teams bring unique expertise and perspectives, sparking ideas that transcend individual limitations. These collective moments yield richer solutions and open doors to unexplored possibilities. Ultimately, engineering innovation is not a sudden flash, but an unfolding process, a dance of curiosity, discipline, and inspiration. It honors tradition while pushing horizons. Turning now from the world of ideas and design, we enter the demanding realm where engineering concepts materialize, manufacturing and construction. This phase translates sketches, calculations, and simulations into tangible objects and structures. The landscape here is rugged and complex. Ideas often meet resistance in the form of material behaviors, process constraints, and human factors. Manufacturing is a delicate balancing act. It requires exact replication of designs within tolerances, sometimes measured in microns, on scales ranging from individual components to massive assemblies. Variability in raw materials, tooling wear, machine calibration, and operator skill can all impact quality. Engineers face challenges in choosing appropriate methods: casting, forging, machining, welding, additive manufacturing, each carrying unique advantages and limitations. Additive manufacturing, or 3D printing, is reshaping possibilities. It permits the building of complex, previously impossible geometries layer by layer. However, controlling defects such as porosity, residual stresses, or imperfect bonding demands precise energy input, material control, and monitoring. Scaling prototypes to industrial production introduces fresh considerations of repeatability, cost, and throughput. Quality control is the backbone of manufacturing success. Techniques range from statistical sampling and process control charts to advanced non-destructive testing, including ultrasonic, radiographic, and thermographic inspections. These tools detect defects invisible to the naked eye and identify early signs of wear or fatigue. Real-time monitoring and automation increasingly enable quick corrections, reducing scrap and downtime. Construction brings its own trials. Unlike controlled factory environments, construction sites are diverse and dynamic. Factors such as weather, logistics, labor conditions, and site geology influence progress and quality. Coordinated sequencing of activities: pouring concrete, erecting steel, installing systems, must minimize conflicts and rework. Construction engineering demands planning, adaptability, and constant communication. Design assists manufacturing and construction through design for manufacturability, DFM, and constructability, DFC principles. These approaches guide designers to optimize shapes, materials, and assembly methods to ease production and installation. Early integration of manufacturing feedback prevents costly redesigns and delays. Supply chains add complexity layers. Sourcing materials and components globally involves fluctuating availability, quality variation, customs regulations, and transportation risks. Disruptions can delay projects or force substitutions requiring requalification. Engineers work closely with procurement, suppliers, and logistics to ensure material flow aligns with schedules and specifications. Safety risks in manufacturing and construction remain a priority. Heavy equipment, hazardous materials, and complex processes pose dangers, mitigated through rigorous training, safety protocols, and engineering controls such as guarding and automation. Occupational health links directly to productivity and project success. Environmental considerations increasingly shape production and construction choices. Waste reduction through recycling, minimizing emissions, conserving water, and reducing energy consumption reflect wider sustainability goals. Life cycle assessments guide decisions toward greener alternatives and certifications such as LEED or ISO standards. Scaling prototypes to full production scale introduces physics and logistics that can confound initial assumptions. Equipment scaling changes heat transfer rates, mixing efficiency, or stress distributions. Process parameters often require re-optimization. Unexpected interactions emerge, mandating ongoing experimentation and monitoring. Complex assemblies depend on supply chain synchronization. Delays or quality issues in a single supplier can cascade through schedules. Just-in-time manufacturing aims to minimize inventory but heightens sensitivity to disruptions. Lean manufacturing techniques, focusing on waste elimination, continuous improvement, and employee empowerment, revolutionize plant efficiency and product quality. Agile methodologies, borrowed from software, enhance responsiveness to changing demands and rapid innovation cycles. In summary, the path from design to built form is a multifaceted endeavor, demanding precision, coordination, adaptability, and foresight. Success requires mastering both technical processes and human systems under variable realities. The complexity of engineering grows exponentially when individual components and systems must come together as a unified whole. Systems integration challenges engineers to orchestrate interdependent elements, mechanical assemblies, electrical networks, software controllers, each designed by specialized teams into cohesive, functioning entities. The difficulties here surge beyond technical detail into coordination, testing, and troubleshooting at scale. Take, for instance, an aircraft. Thousands of parts, from engines and hydraulics to avionics and cabin systems, must operate flawlessly in concert amid extreme conditions. Integrators contend with conflicting interface requirements, timing synchronization, electromagnetic interference, and stringent safety certifications. Mechanical vibrations can affect electronic sensors. Software updates might alter control system responsiveness. Each change ripples unpredictably across interconnected domains. Early-stage integration demands precise communication. Detailed interface control documents, rigorous configuration management, and version tracking mitigate risks of incompatibility. Simulation environments, model interactions, but physical integration often exposes unforeseen issues, misalignments, signal crosstalk, or thermal hotspots. Incremental assembly allows identification of problems at subsystem levels, yet complete system testing remains indispensable. Validation involves exhaustive scenarios replicating expected and unexpected operational conditions. Stress tests, fault injections, and failure mode analyses probe system robustness. Safety-critical industries apply redundant systems and fail-safe architectures to ensure no single fault leads to disaster. Engineering teams document requirements traceability, linking every feature to design elements and test results, supporting certification processes by governing bodies. Software integration adds particular complexity. Different teams often develop code modules in isolated environments and languages. Merging these can reveal incompatibilities, race conditions, or security vulnerabilities. Continuous integration pipelines, automated testing suites, static code analysis, and simulation-based verification become essential tools managing code complexity at scale. Supply chain diversity presents integration risks beyond internal engineering. Variability in component suppliers affects dimensions or electrical characteristics. Software dependencies on third-party libraries may introduce incompatibilities or licensing concerns. Managing this ecosystem requires stringent quality assurance, supplier audits, and contingency planning. Globalization and distributed teams exacerbate coordination challenges. Time zone differences necessitate asynchronous workflows, while cultural and organizational differences require deliberate alignment in communication styles and expectations. Collaborative technologies, shared digital platforms, virtual design reviews, and live data dashboards facilitate transparency but demand disciplined information governance. Human factors remain critical. Operational procedures, maintenance accessibility, and error prevention are integral to system design. Complex interfaces risk user confusion, so usability engineering must simplify human interaction and provide clear diagnostic feedback. The cost of integration failure is enormous. Delays, redesign, or recalls impact schedules and budgets. Conversely, well-executed integration accelerates time to market, ensures reliability, and enhances user confidence. Systems engineering has evolved frameworks such as model-based systems engineering, MBSE, to tame complexity through formalized models and collaborative environments. These approaches formalize requirements, designs, and verification within unified architectures, improving traceability and decision-making. Integration is not a moment, but a process embedded throughout the life cycle, from conceptual design through operation and eventual decommissioning. System upgrades and evolving requirements offer continual integration challenges. In essence, integrating complex systems transcends component engineering. It demands a holistic mindset, meticulous management, and collaborative expertise, bridging technical, managerial, and human domains. In engineering, the margin between success and catastrophe is often razor thin. Safety and reliability are not optional extras. They are non-negotiable pillars that hold the entire discipline upright. Managing risk, anticipating failure modes, and designing resilient systems are paramount challenges engineers face every day. Designing for safety begins with identifying potential hazards, the possible ways a system can fail or behave unexpectedly. Engineers conduct thorough hazard analyses, employing techniques like fault tree analysis, FTA, or failure mode and effects analysis, FMEA, to diagnose vulnerabilities before they manifest. These methods map the chains of events leading to failures, exposing critical points where interventions can prevent disaster. Reliability engineering focuses on ensuring that systems perform consistently over time, despite the stresses and unpredictability of real-world operation. Statistically modeling component lifetimes, material degradation, and usage patterns enables prediction of maintenance needs and replacement schedules. Engineers build in redundancies, backup components, parallel systems to safeguard against single points of failure. In safety-critical fields, such as aerospace, nuclear power, or medical devices, standards and regulations impose rigorous certification procedures. Every design element undergoes exhaustive testing, environmental stress screening, accelerated life testing, vibration and shock assessments. Documentation is meticulous, capturing traceability from requirements through design to validation. Non-compliance carries not only financial penalties, but profound ethical consequences. Human factors engineering enhances safety by designing systems tolerant to operator errors. Controls, alarms, and interfaces are crafted to reduce confusion and fatigue, support quick responses, and prevent accidental misuse. Training and procedures complement engineering solutions in creating comprehensive safety cultures. Risk management in engineering is a balance of probability and consequence. Engineers assess not only how likely a failure is, but how severe its impact would be: physical harm, financial loss, or environmental damage. This risk-based approach guides resource allocation to areas where interventions yield the highest safety returns. Emerging technologies like AI and autonomous systems present new safety frontiers. Engineers must validate not only hardware but complex algorithms operating in uncertain environments. Transparency, explainability, and fail-safe defaults become necessary design considerations. Resilience engineering extends beyond preventing failure to enabling graceful degradation and rapid recovery. Systems are designed to adapt to unforeseen stresses and continue essential functions, or recover quickly when disrupted. Safety also encompasses cybersecurity in modern connected systems. Protecting physical infrastructure from malicious attacks involves integrating encryption, access control, intrusion detection, and robust software development practices. Ultimately, engineering safety demands a proactive, multidisciplinary approach, combining technical rigor, human-centered design, organizational commitment, and continuous learning from incidents. Tonight's exploration unveils how safety and reliability permeate every level of engineering, anchoring innovation to principles that protect lives, assets, and environments. History offers engineers both triumphs to admire and failures to scrutinize, each etched into the fabric of progress. Examining landmark engineering feats and their lessons reveals the relentless trial, error, and evolution embedded in the discipline. Consider the construction of the Brooklyn Bridge, completed in 1883. At that time, bridging the East River challenged the limits of materials, design, and construction techniques. John A. Roebling's vision utilized unprecedented use of steel cable suspension, but tragically, he died early in the project. His son Washington Roebling took charge, himself suffering debilitating illness from working in caissons underwater. Despite adversity, the bridge succeeded through innovation in cable spinning, engineering oversight, and sheer determination. It remains iconic for its architectural beauty and engineering breakthrough in spanning great distances with minimal support. Contrast this with the infamous Tacoma Narrows Bridge collapse. In 1940, nicknamed Galloping Gertie, this suspension bridge dramatically failed just months after opening due to aeroelastic flutter, a sudden wind-induced oscillation. The design was slender, prioritizing aesthetics and cost over aerodynamic stability. This failure reshaped civil engineering by introducing wind tunnel testing and deeper understanding of fluid structure interactions. It starkly illustrated insufficient consideration of dynamic forces can yield catastrophic results. The Apollo 11 moon landing in 1969 epitomizes multidisciplinary engineering mastery, coordinating propulsion, navigation, life support, computing, and materials science under tight timelines amid immense risk pushed boundaries. Redundancies, real-time problem solving, and human ingenuity culminated in astronauts stepping onto another world. The software on the Apollo guidance computer pioneered real-time embedded programming, constrained by severe hardware limits, yet capable of adapting dynamically when alarms triggered during descent. This mission inspired engineering globally and foreshadowed the system's complexity now routine. The Challenger disaster in 1986 shattered NASA's optimistic vision, revealing dangers lurking beneath technical and organizational complexity. An O-ring seal failure in cold temperatures caused explosion shortly after launch. Investigations exposed inadequate risk assessment, communication breakdowns, and pressure to meet schedules, overriding safety concerns. This tragedy emphasized the vital role of transparent engineering ethics, whistleblower protections, and systems thinking encompassing human and institutional factors. In bridge engineering, the Millau Viaduct in France, completed in 2004, represents modern excellence. It soars nearly 270 meters above the Tarn River Valley, the tallest cable-stayed bridge in the world. Advanced materials, precision construction scheduling, and innovative launching techniques enabled erecting slender piers and spanning vast distances with minimal environmental impact. It showcases how combining aesthetics, environmental sensitivity, and cutting-edge technology creates monumental yet harmonious infrastructure. The Deepwater Horizon oil spill in 2010 exposed engineering and regulatory gaps in offshore drilling safety. Equipment failures combined with poor risk management led to a devastating environmental disaster, triggering global scrutiny on engineering design, maintenance, and crisis response in high-risk industries. It drives ongoing efforts to enhance fail-safes, autonomous monitoring, and rapid mitigation capabilities. These examples underscore critical themes: the necessity of understanding physical phenomena in depth, the integration of multi-domain expertise, the acute awareness of risks and trade-offs, and the human organizational context shaping engineering outcomes. Failures impress as deeply as triumphs, outlining boundaries to avoid and prompting advances. Breakthroughs emerge from persistent iteration, bold thinking, and learning from past mistakes. Studying these historic and recent events broadens the engineer's perspective beyond theory, anchoring knowledge in real-world complexity, uncertainty, and consequence. History offers engineers both triumphs to admire and failures to scrutinize, each etched into the fabric of progress. Examining landmark engineering feats and their lessons reveals the relentless trial, error, and evolution embedded in the discipline. Consider the construction of the Brooklyn Bridge, completed in 1883. At that time, bridging the East River challenged the limits of materials, design, and construction techniques. John A. Roebling's vision utilized unprecedented use of steel cable suspension, but tragically he died early in the project. His son Washington Roebling took charge, himself suffering debilitating illness from working in caissons underwater. Despite adversity, the bridge succeeded through innovation in cable spinning, engineering oversight, and sheer determination. It remains iconic for its architectural beauty, an engineering breakthrough in spanning great distances with minimal support. Contrast this with the infamous Tacoma Narrows Bridge collapse in 1940. Nicknamed Galloping Gersie, this suspension bridge dramatically failed just months after opening due to aeroelastic flutter, a sudden wind-induced oscillation. The design was slender, prioritizing aesthetics and cost over aerodynamic stability. This failure reshaped civil engineering by introducing wind tunnel testing and deeper understanding of fluid structure interactions. It starkly illustrated insufficient consideration of dynamic forces can yield catastrophic results. The Apollo 11 moon landing in 1969 epitomizes multidisciplinary engineering mastery. Coordinating propulsion, navigation, life support, computing, and material science under tight timelines amid immense risk, pushed boundaries, redundancies, real-time problem solving, and human ingenuity culminated in astronauts stepping onto another world. The software on the Apollo guidance computer pioneered real-time embedded programming, constrained by severe hardware limits, yet capable of adapting dynamically when alarms triggered during descent. This mission inspired engineering globally and foreshadowed the system's complexity now routine. The Challenger disaster in 1986 shattered NASA's optimistic vision, revealing dangers lurking beneath technical and organizational complexity. An O-ring seal failure in cold temperatures caused explosion shortly after launch. Investigations exposed inadequate risk assessment, communication breakdowns, and pressure to meet schedules overriding safety concerns. This tragedy emphasized the vital role of transparent engineering ethics, whistleblower protections, and systems thinking encompassing human and institutional factors. In bridge engineering, the Millau Viaduct in France, completed in 2004, represents modern excellence. It soars nearly 270 meters above the Tarn River Valley, the tallest cable-stayed bridge in the world. Advanced materials, precision construction scheduling, and innovative launching techniques enabled erecting slender piers and spanning vast distances with minimal environmental impact. It showcases how combining aesthetics, environmental sensitivity, and cutting-edge technology creates monumental yet harmonious infrastructure. The Deepwater Horizon oil spill in 2010 exposed engineering and regulatory gaps in offshore drilling safety. Equipment failures combined with poor risk management led to a devastating environmental disaster, triggering global scrutiny on engineering design, maintenance, and crisis response in high-risk industries. It drives ongoing efforts to enhance fail-safes, autonomous monitoring, and rapid mitigation capabilities. These examples underscore critical themes: the necessity of understanding physical phenomena in depth, the integration of multi-domain expertise, the acute awareness of risks and trade-offs, and the human organizational context shaping engineering outcomes. Failures impress as deeply as triumphs, outlining boundaries to avoid and prompting advances. Breakthroughs emerge from persistent iteration, bold thinking, and learning from past mistakes. Studying these historic and recent events broadens the engineer's perspective beyond theory, anchoring knowledge in real-world complexity, uncertainty, and consequence. Material science stands at the core of engineering innovation, dictating possibilities and imposing constraints on every design. The journey from raw substance to engineered product hinges upon manipulating material properties, processing methods, and microstructures, on scales spanning nanometers to meters. This discipline intertwines chemistry, physics, and mechanics in a quest to create substances tailored for specific applications. Take the development of advanced alloys, a transformative pursuit enabling lighter, stronger, and more durable components. Consider aerospace-grade titanium alloys. Their exceptional strength-to-weight ratios and corrosion resistance make them invaluable in aircraft and spacecraft. Yet titanium's reactivity and high melting point impose manufacturing challenges. Processes like vacuum arc remelting and powder metallurgy have emerged to produce homogeneous, defect-free titanium components essential for safety-critical applications. Ceramic materials reveal another intriguing dimension. Renowned for hardness and thermal resistance, advanced ceramics find roles in turbine blades, biomedical implants, and electronic substrates. However, their inherent brittleness demands overcoming fracture toughness limitations. Innovations such as ceramic matrix composites incorporate reinforcing fibers to hinder crack propagation, marrying strength with damage tolerance. Polymers and composites, characterized by diverse molecular architectures, offer tailorability unparalleled in traditional materials. Carbon fiber reinforced polymers, CFRP for example, combine lightweight profiles with exceptional tensile strength, revolutionizing sectors like automotive and aerospace. The anisotropic nature of composites requires precise fiber orientation to optimize load paths, demanding sophisticated design tools and quality assurance protocols to prevent delamination or premature failures. Nanotechnology pushes boundaries further by engineering materials at atomic and molecular scales. Carbon nanotubes and graphene showcase extraordinary electrical conductivity, mechanical strength, and thermal properties, promising next-gen sensors, electronics, and structural reinforcements. Manipulating these materials involves mastering complex synthesis methods and controlling defect densities that profoundly impact performance. Thermal management remains a vital consideration influencing material selection. High-performance electronics, or jet engines operate under extreme temperatures where thermal expansion mismatches between adjacent materials can induce stresses and warping. Engineers employ heat-resistant alloys, ceramics, or phase-change materials to dissipate heat efficiently while maintaining dimensional stability. Surface engineering techniques enhance material functionality, extending lifetimes and introducing capabilities like wear resistance, corrosion protection, or biocompatibility. Methods such as physical vapor deposition, PVD, chemical vapor deposition, CVD, and laser surface treatment create thin, uniform coatings tailored to environmental demands. These technologies enable components to endure abrasive environments or biologically hostile conditions. Material aging, degradation, and environmental interactions impose another layer of complexity. Polymers exposed to UV radiation can embrittle. Metals may corrode in saline atmospheres. Composites can undergo matrix cracking under fatigue. Predicting these behaviors involves accelerated weathering tests and multi-scale simulations to formulate maintenance schedules and replacement intervals that ensure safety and efficiency. Sustainability drives emerging material research intensely. Development of bio-based polymers, recyclable composites, and low-energy processing methods responds to environmental imperatives and circular economy goals. Engineers must balance these considerations with performance criteria and economic viability. Manufacturability and scalability constitute persistent challenges in material innovation. Laboratory successes demand translation to commercial production, often requiring new equipment, quality control protocols, and supply chain logistics. Unexpected scaling effects, such as grain growth or phase segregation, may degrade properties, necessitating iterative refinement. Ultimately, material science empowers engineering breakthroughs, but demands an intimate understanding of multifaceted behaviors across scales and environments. It is a field of continual interrogation into the nature of matter, unlocking enhanced capabilities while confronting perpetual trade-offs. This part of the journey reveals how materials enable every engineered creation, from massive infrastructure to microscopic devices, anchoring potential within the constraints of physical reality. The digital revolution has transformed engineering from a primarily physical craft into a complex fusion of computation, design, and control. Today, digital tools permeate nearly every phase of engineering workflows, from initial concept sketches to final product testing, enabling levels of precision and complexity unimaginable just decades ago. At the core of this transformation is computer-aided design, or CAD. Modern CAD software provides detailed, three-dimensional modeling capabilities that allow engineers to visualize forms, simulate motion, and analyze structural performance early in the design process. Parametric and feature-based modeling techniques enable rapid iteration, where dimensions and relationships adjust automatically in response to design changes, dramatically accelerating development cycles. Building upon CAD, computer-aided engineering CAE tools allow finite element analysis FEA and computational fluid dynamics CFD to predict stresses, heat flow, and fluid behavior within virtual prototypes. Instead of building costly physical models at every stage, engineers validate performance, identify flaws, and optimize designs digitally. This simulation-driven approach saves time and resources while expanding exploration into extreme scenarios, high loads, crash impacts, or turbulent airflow, potentially too dangerous or expensive to replicate experimentally. Digital twin technology represents a leap forward by creating real-time virtual replicas of physical assets or systems, continuously fed by sensor data. This live mirror enables predictive maintenance, operational optimization, and scenario testing, without interrupting actual operations. Industries ranging from aerospace to manufacturing deploy digital twins to extend asset life and reduce downtime with precision monitoring. Automation in manufacturing, catalyzed by digital control systems, robotics, and additive processes, ensures unparalleled repeatability and complexity in production. Programmable logic controllers, PLCs, orchestrate assembly lines with millisecond accuracy, coordinating thousands of moving parts in synergy. Industrial robots perform welding, machining, and inspection, while advanced vision systems detect microscopic defects, ensuring quality control surpasses human capabilities. Integration of machine learning and artificial intelligence into engineering workflows opens new frontiers. Algorithms now assist in design optimization by exploring parameter spaces too vast for manual method, discovering configurations maximizing strength, weight, or efficiency. AI-powered fault diagnostics analyze vast operational data streams to predict failures before they occur, enabling preemptive interventions that prevent costly breakdowns. Despite these advances, digital engineering introduces challenges. Data interoperability across diverse software and hardware platforms poses persistent hurdles. Engineering teams must manage version control meticulously to ensure design consistency amid rapid changes. Cybersecurity emerges as a critical concern, where threats to intellectual property or industrial control systems require robust defense mechanisms integrated into engineering processes. Human expertise remains essential. Digital tools augment, not replace, the engineer's judgment and creativity. The ability to interpret complex simulation results, validate assumptions, and understand contextual constraints ensures that reliance on computation contributes effectively to safe and innovative outcomes. Training the engineering workforce for this hybrid environment demands expanded skill sets, blending domain knowledge with programming, data analysis, and digital collaboration capabilities. Virtual and augmented reality increasingly support education and remote teamwork, breaking geographical barriers and enhancing understanding through immersive experiences. Cloud computing and high-performance computing infrastructures enable handling of massive datasets and simulations, accelerating iterative design cycles and collaborative problem-solving across global teams. As these technologies evolve, ethical considerations surface around automation's impact on jobs, responsibility in AI-driven decisions, and transparency of complex software on critical infrastructure. Digital engineering reshapes what is possible, while introducing layers of complexity requiring new management philosophies. This chapter of engineering epitomizes the interplay of innovation with practical constraints, reflecting a dynamic balance of technological opportunity, human insight, and organizational agility. The global imperative to address climate change and resource scarcity thrusts sustainable engineering into the spotlight as one of the most critical challenges facing the discipline. Designing energy systems that balance reliability, cost, and environmental responsibility pushes engineers to rethink traditional paradigms. Emerging technologies promise transformative solutions, but introduce distinct hurdles rooted in materials, integration, and variability. Renewable energy sources, solar, wind, hydro, geothermal, form the backbone of this transition. Photovoltaic solar panels, fundamentally semiconductor devices converting sunlight to electricity, have seen efficiency improvements propelled by material science innovations such as perovskite layers and multi-junction cells. Scaling production while maintaining performance and durability against degrading influences like UV exposure and temperature cycling remains a central engineering concern. Wind turbines exploit atmospheric motion, converting kinetic energy into electrical power. Aerodynamic blade design, structural dynamics, and fatigue resistance define turbine longevity and productivity. Modern designs involve blades stretching over 80 meters, constructed from composites resistant to cyclic loads and environmental erosion. Engineering challenges center on optimizing energy capture while minimizing noise, environmental footprint, and maintenance needs, often at remote or offshore sites hostile to regular servicing. Storage solutions constitute a major bottleneck for renewable integration due to intermittency. Battery technologies, notably lithium-ion, dominate current applications but face limitations in capacity, lifespan, charging rates, and raw material ethics. Alternative approaches including solid-state batteries, flow batteries, and hydrogen fuel cells represent active research frontiers. Each demands breakthroughs in chemistry, manufacturing scalability, safety, and cost optimization. Grid systems must evolve from centralized distribution models to smart, decentralized, and resilient networks capable of accommodating dynamic power flows and two-way transactions. Power electronics, advanced sensors, and communication infrastructure enable real-time monitoring and adaptive control to match supply with stochastic demand. This cyber-physical complexity mandates multidisciplinary engineering expertise spanning electrical, computer, and systems domains. Efficiency improvements in traditional energy systems remain pertinent. Carbon capture and sequestration technologies aim to mitigate existing fossil fuel impacts, but face engineering barriers related to scalability, energy consumption, and geological stability. Nuclear energy, with high energy density and low carbon emissions, confronts public acceptance and safety challenges, driving advances in small modular reactors and fusion research. Embedded sustainability criteria extend beyond energy generation into building materials, transportation systems, and industrial processes. Life cycle assessments (LCA) inform design decisions, accounting for embodied carbon, recyclability, and pollutant emissions across product lifespans. Circular economy principles promote reuse and waste reduction, but demand novel design methodologies and supply chain reconfiguration. Environmental engineering addresses pollution control and remediation. Techniques such as advanced filtration, biological treatment, and chemical neutralization safeguard water and air quality. The interplay between engineered systems and natural ecosystems requires integrating ecological knowledge with technological solutions. Climate resilience engineering prepares infrastructure and communities for increasingly frequent extreme events. Floods, heat waves, storms. Innovations include adaptive building designs, flood barriers, and resilient communication networks designed to sustain functionality under duress. Engineering responses must respect social contexts and equity concerns, ensuring vulnerable populations receive protection. The sustainability transition demands rapid innovation, combined with robust regulatory frameworks, interdisciplinary collaboration, and sophisticated modeling to predict impacts and optimize solutions amid uncertainty. Engineering in this domain is a multifaceted pursuit of harmonizing human development with planetary boundaries, transforming challenges into opportunities through rigorous science and creative application. Engineering, often viewed through the lens of physics and technology, extends far beyond equations and machines into a complex tapestry of social, economic, and ethical dimensions. Large engineering projects, whether building a dam, launching a satellite, or developing urban transport systems, navigate intricate socio-technical landscapes that demand balanced governance and holistic planning. At the forefront lies governance of engineering endeavors. Decision-making structures integrate technical experts, policymakers, financiers, and community stakeholders, all with distinct priorities and languages. Effective governance accounts for competing interests, risk assessments, regulatory compliance, and public accountability. The challenge is developing transparent processes where decisions are made collaboratively yet efficiently, especially when projects span multiple jurisdictions and cultures. Economics profoundly shape engineering outcomes. Funding allocations dictate which projects succeed or fail. Cost-benefit analyses incorporate not only direct expenses and revenues, but also intangible social value and environmental impacts. Engineers must consider life cycle costs, including maintenance, decommissioning, and externalities like pollution or displacement, pricing infrastructure services fairly, while ensuring access to underserved populations amplifies complexity. Ethics form the backbone of responsible engineering. Beyond technical competency, practitioners engage with questions of safety, equity, privacy, and sustainability. For instance, introducing automated surveillance technologies entails navigating tensions between security benefits and individual rights. Engineering judgments influence human lives, requiring deep reflection on moral responsibilities, societal consequences, and transparency of risk. Public engagement transforms engineering from expert-driven to participatory. Meaningful consultation, co-design, and community involvement enable projects to respond to local needs, values, and knowledge. Managing diverse expectations, managing misinformation, and handling conflicts within stakeholder groups test communication, negotiation, and conflict resolution skills. Infrastructure projects face environmental justice considerations. Marginalized or vulnerable communities often bear disproportionate impacts of pollution, displacement, or noise. Engineers and planners must integrate social equity principles, striving to distribute benefits and burdens fairly. Tools such as geographic information systems, GIS, help visualize spatial inequities, informing more just decisions. Regulatory landscapes add further intricacies. Compliance with safety codes, environmental regulations, intellectual property laws, and labor standards requires coordination across agencies. Shifts in political priorities or legislation can stall projects or impose costly redesigns. Anticipating regulatory trends becomes an essential dimension of project planning. Risk perception by the public may diverge from technical assessments. The acceptability of risks depends on cultural factors, trust in institutions, and prior experiences. Effectively communicating uncertainties, limitations, and mitigation strategies fosters informed consent, crucial for project legitimacy. The complexity amplifies in global megaprojects such as international space stations, transnational pipelines, or urban megadevelopments. Coordinating multinational teams, managing currency fluctuations, geopolitical tensions, and logistical hurdles tests leadership and adaptability on unprecedented scales. Technology itself reshapes socio-technical relationships. Digital platforms enable crowdsourcing ideas, monitoring environmental compliance remotely, and fostering decentralized energy trading. These innovations democratize aspects of engineering but challenge traditional control structures. Educational and professional development programs increasingly incorporate these socio-technical components, embedding ethics, communication, and policy studies alongside technical curricula. Multidisciplinary collaboration becomes a norm rather than exception. In short, engineering is embedded in society's fabric, influencing and influenced by politics, culture, and economics. Mastering these dimensions requires engineers to be not just problem solvers, but facilitators, negotiators, and visionaries, capable of guiding complex systems towards sustainable and equitable futures. This dimension of engineering demands no shortcuts, careful contextual analysis, and a commitment to serving the broader human good. Engineering is fundamentally a collective endeavor, and no amount of technical brilliance alone guarantees success without effective leadership, teamwork, and communication. In today's fast-paced, interconnected, and multidisciplinary environments, these human skills stand as critical pillars sustaining innovation, quality, and resilience. Leadership in engineering diverges sharply from traditional hierarchical management. It demands situational awareness, the ability to sense changing technical, environmental, and social conditions, and the emotional intelligence to motivate diverse teams facing complex ambiguity and pressure. Effective leaders cultivate environments where expertise flourishes alongside open dialogue, proactive problem solving, and shared ownership of challenges and successes. Unlike clear-cut directives, contemporary engineering leadership often operates less by command and more through influence, coaching, and facilitation. Leaders must reconcile short-term goals with long-term vision, balancing competing priorities such as safety, budget, schedule, and innovation risk. They also mediate between stakeholders having conflicting interests, from clients demanding cost efficiency to regulators mandating stringent safety constraints. Moreover, technical credibility remains indispensable for gaining trust and guiding sound decisions. Leaders deeply understand core principles, permitting them to make informed judgments, challenge assumptions, and evaluate risks despite uncertainty. This blend of competence and empathy differentiates outstanding engineering leaders capable of steering projects through turbulence. At the heart of any engineering project lies collaboration. Teams rarely consist of homogeneous experts. Rather, they assemble cross-disciplinary specialists, contractors, suppliers, and end users. Each stakeholder operates within domain-specific jargon, mental models, and priorities. Bridging these gaps requires deliberate efforts fostering mutual understanding and respect. Collaboration techniques range from structured interdisciplinary design reviews to informal knowledge-sharing sessions. Visual tools, diagrams, mock-ups, shared digital platforms help align disparate mental models into collective visions. Iterative prototyping activities invite feedback early and continuously, avoiding the pitfalls of siloed, linear workflows. Distributed and globalized teams multiply complexities through different cultural norms, communication styles, and time zones. Successful collaboration counters these barriers with explicit protocols for communication, conflict resolution, and decision-making. Investing in team cohesion through frequent touch points, clarity of roles, and social bonding enhances trust and coordination. Communication, both internal and external, acts as a lifeline. Within teams, clear, transparent information exchange enables swift identification of issues and agile response. Transparency about uncertainties, assumptions, and trade-offs encourages inclusive problem solving and reduces costly misunderstandings. Externally, engineering projects intersect with diverse audiences, regulators, clients, communities, media, each with unique information needs and comprehension levels. Translating complex technical content into accessible language without compromising accuracy demands skill and empathy. Thoughtful storytelling contextualizes decisions, clarifies risks, and builds confidence. Digital collaboration tools enhance communication possibilities, but underscore the need for disciplined information management. Overload, misinterpretation, and reduced personal interaction require strategies combining synchronous meetings, asynchronous updates, and informal channels. Recording decisions and rationale supports accountability and continuity amid personnel changes. Conflict is inevitable, but when managed constructively, catalyzes superior outcomes by surfacing dissent, revealing hidden assumptions, and fostering critical reflection. Engineering leaders and teams adopt conflict resolution styles, blending assertiveness with openness, seeking integrative rather than adversarial solutions. Emotional resilience underpins sustained performance amid the inevitable pressures, setbacks, and uncertainty. Organizations committed to psychological safety promote environments where individuals feel valued and supported, enabling risk-taking, learning, and creativity. Training and professional development programs increasingly prioritize these soft skills alongside technical mastery. Mentorship, coaching, leadership workshops, and simulation exercises develop communication, negotiation, and cultural competence crucial in modern engineering. The evolving nature of engineering challenges, from wicked problems to socio-technical systems, positions leadership, collaboration, and communication not as adjuncts, but as integral competencies, shaping every phase of the engineering lifecycle. In this light, engineering becomes both a technical and profoundly human art, crafting not only devices and infrastructure, but relationships, trust, and shared purpose that propel innovation and resilience. Mastering this human core is not simple or swift. It demands continuous reflection, adaptation, and courageous humility. Yet it is where the greatest engineering challenges are met and surpassed. This final chapter honors the often invisible but vital forces that transform isolated calculations and components into functioning, sustainable, and impactful realities. Engineering marvels often hide their complexity beneath seemingly simple appearances. Take the humble escalator, a device that carries millions daily, yet embodies a symphony of mechanical precision, safety controls, and user interaction design. The steps are linked in an endless chain, cycling smoothly on tracks guided by gears, powered by motors, calibrated for continuous operation. Safety sensors detect obstructions and adjust speed or stop movement instantly, preventing accidents. Behind this familiar convenience lies extensive engineering focused on durability, energy efficiency, and user comfort. Another fascinating domain is micro-electromechanical systems, or MEMS. These devices integrate tiny mechanical elements, sensors, actuators, and electronics on silicon chips, measuring less than a millimeter. MEMS find applications from airbags deploying in milliseconds during collisions to precision medical devices navigating human vessels. Engineers face challenges at this scale due to forces that dominate at micro levels, like surface tension and electrostatic interactions. Fabrication techniques resemble those used for microchips, but must accommodate moving parts, requiring innovative etching, deposition, and packaging methods. In fluid dynamics, the tiny droplets forming fog or raindrops follow principles that influence engineering designs ranging from inkjet printers to fuel injectors. The atomization process, breaking a liquid column into fine droplets, depends on nozzle geometry, fluid properties, and ambient conditions. Understanding these behaviors allows engineers to optimize spray patterns for agricultural pesticides, combustion efficiency, or medical aerosols. The invisible dance of surface tension and aerodynamic forces determines how droplets form, coalesce, or evaporate, revealing intricate physics harnessed through precise engineering. The worldwide network of tunnels and subways represents vast underground engineering challenges. Engineers contend with geological heterogeneity, groundwater inflows, and urban congestion. Techniques include tunnel boring machines, TBM, advancing through rock while installing segmented linings, or cut and cover methods excavating from the surface. Ventilation, fire safety, and evacuation planning incorporate dynamic simulation models predicting airflow and smoke movement. Integration with surface transportation systems demands coordination with civil and electrical engineering disciplines, creating seamless urban mobility solutions. Precision timing systems underpin modern engineering's heartbeat. Atomic clocks utilizing oscillations of cesium or rubidium atoms achieve accuracies of parts per trillion, enabling GPS navigation, telecommutation synchronization, and scientific experimentation. The engineering of these devices delves deep into quantum physics, vacuum technologies, and signal processing. Even slight timing errors cascade into significant systemic inaccuracies, highlighting the delicate interplay between fundamental science and applied engineering. The textile industry blends ancient craft with cutting-edge engineering. Modern fabrics incorporate microfibers, nanocoatings, and embedded sensors to create materials that repel water, regulate temperature, or monitor health metrics. Engineering processes like spinning, weaving, and knitting are continuously optimized through robotics and automated quality control. Advanced polymers introduce flexibility and durability while minimizing environmental footprints, challenging engineers to balance functionality with sustainability. In geothermal engineering, Extracting Earth's heat for power generation or heating necessitates understanding subterranean geology, fluid rock interactions, and thermal transport. Engineers design wells to access hot water or steam reservoirs kilometers underground, managing high pressures and corrosive fluids. Enhanced geothermal systems create artificial reservoirs by fracturing rock formations, requiring meticulous monitoring to prevent induced seismicity. Integrating geothermal energy into existing grids demands innovative control and storage strategies to accommodate variability. The space industry epitomizes extreme engineering conditions. Rockets must endure intense combustion temperatures, rapid acceleration, and vacuum conditions. Material selection balances weight reduction with thermal protection and vibration damping. Guidance systems rely on inertial navigation combined with real-time telemetry. Satellites integrate communication, imaging, and propulsion subsystems within tight size and power constraints. Launch windows depend on celestial mechanics, orbital dynamics, and atmospheric conditions, illustrating engineering's deep connection with natural laws. These snapshots barely scratch the surface of modern engineering's vast scope. Each fact or system carries an abundance of specialized knowledge, precision techniques, and innovative problem solving. Diving into the world of renewable energy storage technologies reveals a critical frontier where engineering innovation directly affects the feasibility of sustainable power systems. Conventional lithium-ion batteries remain widespread, but face limitations in raw material supply, energy density, and safety concerns. Engineers are exploring alternative chemistries such as sodium-ion, solid-state batteries, and flow batteries that offer distinct advantages and unique challenges. Sodium-ion batteries leverage abundant sodium resources, potentially reducing costs and environmental impact. However, sodium ions are larger and heavier than lithium ions, complicating electrode design and energy density optimization. Material engineers innovate nanostructured electrodes and novel electrolytes to improve charge cycling and lifespan, applying advanced characterization techniques to monitor degradation mechanisms at the atomic scale. Solid-state batteries replace the liquid electrolyte with solid materials, reducing leakage and flammability risks. Their higher voltage tolerance and theoretical energy capacity promise significant leapfrogging in electric vehicle range and consumer electronics. Yet, fabricating solid electrolytes with high ionic conductivity and mechanical flexibility requires breakthroughs in ceramics, polymers, or hybrid materials. Interface resistance between electrodes and solid electrolytes remains a persistent engineering puzzle. Flow batteries operate by circulating liquid electrolytes through electrochemical cells, allowing scalable energy storage, independent of power capacity. They are attractive for grid-scale storage due to rapid response times and long cycle life. Engineering focuses on optimizing membrane selectivity, flow dynamics, and stack configurations to improve efficiency and reduce costs. Integration with fluctuating renewable sources demands sophisticated control software, managing charge-discharge cycles and state of charge estimation. Hydrogen energy also plays a pivotal role in emerging storage and energy carrier concepts. Production methods, such as electrolysis powered by renewables, create green hydrogen, which in turn can be stored and transported for use in fuel cells or combustion. Engineering challenges include developing catalysts with high efficiency and durability, building safe storage tanks resistant to embrittlement, and constructing infrastructure for distribution. In construction engineering, advances in modular and prefabricated building techniques enhance speed, quality control, and sustainability. Precision engineered modules manufactured off-site assemble rapidly on-site, minimizing weather-related delays and waste. Structural connections and utilities coordination demand rigorous quality assurance, 3D modeling, and standardization to ensure seamless integration. This method revolutionizes housing and commercial construction, addressing labor shortages and environmental concerns. The aviation industry pushes boundaries with hybrid electric propulsion systems, aiming to reduce carbon footprint and noise pollution. These designs integrate electric motors, batteries, and traditional engines with intricate power management architectures. Lightweight materials and cooling systems for batteries and electronics become critical engineering targets. Safety certification processes impose stringent requirements on redundancy, fault tolerance, and electromagnetic compatibility. In robotics, engineers develop autonomous systems able to operate in unstructured environments. Algorithms synthesize sensor data from LiDAR, cameras, and inertial measurement units to navigate complex settings. Mechanical design balances dexterity, strength, and energy efficiency tailored to tasks from manufacturing automation to planetary exploration. Human-robot interaction interfaces incorporate gesture recognition and voice commands, advancing usability and collaborative potential. Biomedical engineering merges life sciences and mechanical principles to create sophisticated devices, prosthetics with neural control, implantable sensors monitoring biochemical states, and tissue engineering scaffolds promoting regeneration. Biocompatibility, sterilization, and power autonomy present engineering constraints requiring material innovation, miniaturization, and wireless communication. Wireless power transfer offers transformative possibilities for charging devices without cords. Techniques include inductive coupling, resonant magnetic fields, and microwave transmission. Engineers optimize coil geometry, frequency management, and electromagnetic shielding to maximize efficiency and safety, enabling applications from consumer electronics to electric vehicle charging. Water treatment engineering employs advanced membrane filtration, UV disinfection, and chemical oxidation to provide safe and potable water. Engineers optimize flow rates, fouling control, and energy consumption, balancing treatment, efficacy, and operational cost. Developing affordable, scalable solutions is vital for global health equity. These frontiers illustrate engineering's evolving landscape, where multidisciplinary knowledge, advanced materials, automation, and sustainability coalesce to address complex challenges. Transportation engineering underpins the movement of goods and people, shaping economies, urban landscapes, and daily life. Stretching from traditional roadways to avant-garde hyperloop concepts, this field encompasses structural design, traffic flow analysis, vehicle dynamics, and emerging technologies, all orchestrated to optimize efficiency, safety, and sustainability. Highway engineering begins with geometric design, the alignment and cross-section of roads tailored to terrain, vehicle speeds, and safety standards. Engineers calculate sight distances, super elevation on curves, and lane widths to accommodate vehicle dynamics and driver behavior. Material selection for pavements involves balancing initial cost, durability, skid resistance, and maintenance demands. Asphalt mixtures employ specialized binders and aggregates, fine-tuned for local climate and traffic loads. Concrete pavements incorporate reinforcing fibers and curing protocols, ensuring longevity and resistance to cracking. Traffic engineering integrates principles of flow theory, signal timing, and queuing analysis. Modeling techniques leverage microscopic simulations tracking individual vehicle movements to optimize intersections and reduce congestion. Adaptive traffic control systems use real-time sensor inputs and algorithms to adjust signal phases, smoothing traffic and reducing emissions. Pedestrian and cyclist safety become pivotal concerns addressed through crosswalk design, visibility enhancements, and traffic calming measures. Railway engineering encompasses track design, vehicle dynamics, and signaling systems. Track geometry combines rail profiles, ties, ballast, and subgrade considerations supporting dynamic train loads at high speeds. Engineers optimize rail cross-sections and welding techniques to minimize fatigue and noise. Signal systems have evolved from fixed block to advanced moving block communications-based train control, enabling higher capacity and safety. Electrification infrastructure introduces challenges in power delivery and electromagnetic compatibility. Air transportation engineering involves airport runway layouts, air traffic management, and aircraft ground operations. Runways must accommodate takeoff and landing forces, with robust pavement structures, drainage systems, and friction characteristics for diverse weather. Lighting and instrument landing systems enhance safety during adverse visibility. Managing airspace with increasing traffic demands distributed control centers, collision avoidance algorithms, and integrated scheduling software, balancing efficiency and environmental noise constraints. Emerging transport modalities like high-speed rail push engineering into new regimes. Track tolerances tighten. Aerodynamic phenomena such as tunnel micropressure waves arise, and vibration control demands innovative dampening technologies. Construction materials and methods evolve to maintain track stability despite thermal expansion and heavy cyclic loads. The Hyperloop concept exemplifies visionary engineering, proposing near supersonic travel in low-pressure tubes. This system involves vacuum maintenance, magnetic levitation, and linear motor propulsion. Engineering challenges span tube structural integrity, passenger safety during rapid acceleration, thermal management, and emergency evacuation procedures. The integration of control systems, energy storage, and maintenance strategies remains under active development, showcasing interdisciplinary engineering frontiers. Urban transportation planning addresses complex multimodal integration, land use, and social equity. Engineers design transit networks, optimizing accessibility, capacity, and service reliability using demand forecasting and spatial analysis. Intelligent transportation systems integrate data from connected vehicles and infrastructure, enabling dynamic routing and enhanced safety features. Sustainability increasingly guides transportation engineering. Electrification of vehicles requires charging infrastructure and grid capacity enhancements. Materials recycling, noise pollution mitigation, and life cycle emissions assessments influence design choices. Public transportation systems emphasize energy efficiency and equitable service provision, balancing operational cost with societal benefit. Freight transportation combines infrastructure design with logistics optimization. Intermodal terminals manage transfers among road, rail, air, and sea shipments. Engineers employ real-time tracking, automated container handling, and predictive maintenance to enhance throughput and reliability. In all domains, transportation engineering relies on data analytics, machine learning, and sensor networks to make systems smarter, safer, and more responsive. Cybersecurity and privacy concerns emerge as critical considerations in connected and autonomous vehicles. From macroscopic infrastructure to microscopic control algorithms, transportation engineering navigates a web of technical, environmental, and societal factors, an evolving orchestra driving human progress. Smart cities represent the next frontier where engineering integrates information technology, urban planning, and civil infrastructure to create efficient, livable, and sustainable environments. These urban ecosystems rely on interconnected sensors, communication networks, data analytics, and automation, creating cyber-physical systems, optimizing resource use, and enhancing citizens' quality of life. At the core of smart city engineering lies the deployment of vast sensor networks, collecting real-time data on air quality, traffic, energy consumption, water distribution, and waste management. This data feeds centralized and distributed computing platforms that analyze patterns, predict demands, and automate responses. For example, adaptive street lighting dims during low pedestrian activity to save energy while enhancing safety during peak times. Water management systems leverage smart sensors to detect leaks instantly, regulate flow based on demand, and maintain water quality through continuous monitoring of chemical and biological parameters. Engineers design actuators integrated into pipelines, valves, and pumps that respond autonomously or upon remote commands, maintaining efficient and reliable supply. Transportation networks within smart cities incorporate real-time traffic data, public transit schedules, and pedestrian flows. Multimodal journey planning applications provide citizens real-time alerts and route suggestions, improving mobility and reducing congestion. Vehicle-to-infrastructure communication facilitates coordinated traffic signals, adjusting dynamically to traffic volumes, and emergency vehicle prioritization. Energy systems decentralize through distributed generation assets like rooftop solar panels and battery storage. Grid management integrates demand response programs, incentivizing consumers to shift usage away from peak hours. Engineers design microgrids managing localized generation and storage, enhancing resilience against outages and optimizing renewable integration. Waste management employs sensor-equipped bins that monitor fill levels and optimize collection routes, reducing unnecessary pickups and emissions. Recycling processes benefit from automated sorting using robotics and AI-enabled visual recognition systems, increasing recovery rates while minimizing contamination. The backbone of smart cities includes robust telecommunication infrastructure, embracing 5G and beyond, supporting the vast data transfer demands and low latency necessary for critical applications like autonomous vehicles and remote healthcare. Engineers secure these networks against cyber threats and design redundancy to assure availability under varied conditions. From a structural perspective, civil engineering innovations embed sensors into bridges, roads, and buildings, creating smart structures capable of self-monitoring vibrations, stresses, temperature changes, and material degradation. Data collected enables predictive maintenance, extending asset lifespans and preventing catastrophic failures. Urban design integrates green infrastructure, bioswales, green roofs, permeable pavements, mitigating flooding risks, and improving air quality. These elements require interdisciplinary collaboration balancing aesthetics, ecology, hydrology, and engineering constraints. Public safety improves through integrated surveillance, emergency response coordination, and environmental hazard detection systems. Engineering designs prioritize privacy through data anonymization, access controls, and transparent policies, responding to societal concerns. The complexity of coordinating heterogeneous systems leads to increased importance of standards, interoperability, and open data initiatives. Engineers implement modular, scalable architectures supporting incremental upgrades and integration of emerging technologies. Sustainability targets permeate every aspect, from reducing urban heat islands via material choices and vegetation to promoting walkability and active transportation through urban layout. Engineering solutions thus intertwine closely with social policies, economics, and public engagement. Smart city engineering embodies a grand synthesis, melding infrastructure, technology, environment, and society. It navigates ambitious goals of equity, resilience, and innovation amidst challenges of system complexity, data security, and human factors. Aerospace engineering stands at the pinnacle of technical challenge and innovation, pushing the limits of physics, materials, and precision under extreme conditions. From subsonic aircraft to interplanetary spacecraft, the field demands mastery of aerodynamics, propulsion, structures, avionics, and systems integration, all evolving dynamically with technological progress. One of the key breakthroughs shaping modern aerospace is the development of advanced propulsion systems. Traditional jet engines achieve thrust by compressing and combusting air, then accelerating exhaust gases. Engineers have incrementally improved efficiency through high bypass turbofans and variable cycle engines, balancing fuel consumption noise reduction, and power output. However, the quest for supersonic and hypersonic travel spurs research into alternative technologies such as scramjets, engines that combust fuel in supersonic airflow, enabling speeds exceeding Mach 5. Designing scramjets involves mastering phenomena like shockwave boundary layer interactions and temperature-induced material degradation at thousands of degrees Celsius. Rocket propulsion embodies radically different principles. Rockets carry both fuel and oxidizer, providing thrust independent of atmospheric oxygen for space travel. Chemical rockets optimize combustion stability, cooling, and thrust-to-weight ratios. New developments emphasize reusable engines, exemplified by variable thrust capabilities and regenerative cooling channels where fuel absorbs engine heat before combustion. Electric propulsion systems like ion thrusters offer high efficiency and precision for satellite station keeping and deep space missions, despite producing lower thrust requiring prolonged operation. Structural engineering in aerospace balances three core demands: minimizing weight, resisting extreme loads, and ensuring reliability. Advanced composites now dominate aircraft fuselages and wings due to their superior strength-to-weight ratios and fatigue tolerance. Carbon fiber reinforced polymers reduce weight significantly, improving fuel efficiency and range. Yet these materials demand complex manufacturing processes, precise fiber alignment, curing cycles, and damage inspection using ultrasonic or thermographic methods. Metal alloys such as titanium and aluminum lithium also retain niche roles where toughness and formability are prioritized. Aerodynamics is a science and art of shaping aircraft surfaces to manipulate airflows, minimizing drag while maximizing lift and stability. Computational fluid dynamics (CFD) has revolutionized this domain, enabling engineers to simulate complex turbulent flows over entire aircraft geometries. Wind tunnels remain essential for validating models and capturing subtle flow phenomena like vortex shedding and shockwave formation at transonic speeds. Laminar flow control technologies seek to maintain smooth airflow over wings, reducing drag and improving efficiency, but require extraordinary surface smoothness and active control methods. Avionics integrate a vast array of sensors, computers, and communication devices, coordinating navigation, flight control, and systems monitoring. Fly-by-wire architectures replace traditional mechanical controls with electronic input-output chains, increasing reliability through redundancy and enabling sophisticated automatic stabilization and maneuvering algorithms. Emerging artificial intelligence promises adaptive autopilots capable of autonomously handling irregular conditions, potentially enhancing safety and operational flexibility. Thermal management poses significant challenges. High-speed flight generates heat through aerodynamic friction, necessitating heat-resistant materials and active cooling. Spacecraft face extreme temperatures and radiation, requiring multi-layer insulation, radiators, and heat pipe technologies. Cryogenic fuel storage, essential for rockets, demands specialized tanks, minimizing boil-off and maintaining structural integrity under thermal cycling. Systems engineering orchestrates the myriad aerospace components to produce coherent, safe, and high-performance platforms. Integration tests verify electrical, mechanical, software, thermal, and control subsystems work seamlessly. Maintenance planning leverages condition monitoring sensors, predicting wear and fatigue, optimizing inspection and repair schedules. Safety analyses use probabilistic risk assessment, quantifying failure likelihood and impact, applying stringent certification processes. Aerospace engineering also confronts sustainability pressures. Efforts to reduce carbon emissions stimulate research in sustainable aviation fuels, hybrid electric propulsion, and optimized operational procedures, minimizing fuel burn. Noise pollution control benefits from engine design innovations and flight path adjustments. Design to manufacture pipelines. leverage digital twins replicating aircraft and rocket subsystems, enabling virtual testing and anomaly diagnosis prior to physical assembly. Additive manufacturing produces complex lightweight parts, including engine components with internal cooling channels impossible via conventional methods. Launch vehicle engineering embodies integration of propulsion, payload accommodation, thermal protection, and ground support infrastructure, a tremendous choreography under strict weight, volume, and reliability constraints. Innovations in reusable rockets and miniaturized satellites democratize space access but require redefining design and operational philosophies. The aerospace sector exemplifies how convergent engineering disciplines confront extremes of environment, performance, and precision. Its continuous breakthroughs reshape transport, communication, exploration, and defense globally. Artificial intelligence and machine learning now serve as transformative forces reshaping engineering across disciplines, ushering in new possibilities while introducing novel complexities. These technologies extend traditional engineering methods by automating pattern recognition, optimizing design spaces, predicting system behaviors, and augmenting decision-making through data-driven insights. Machine learning algorithms analyze massive data sets arising from simulations, experiments, and sensor networks that surpass human comprehension. In structural engineering, for instance, AI models predict fatigue life and failure points by correlating microstructural data, load histories, and environmental variables. These predictive analytics enable optimized maintenance schedules and proactive repairs, dramatically improving safety and reducing costs. Design optimization benefits extensively from evolutionary algorithms and generative design techniques. Engineers input performance criteria, constraints, and material properties. AI algorithms explore an expansive solution space, iteratively crafting innovative geometries or configurations often beyond human imagination. Resulting designs exhibit improved strength-to-weight ratios, minimized material usage, or enhanced thermal management. This capability accelerates development cycles and fosters sustainable engineering. Control systems gain sophistication through reinforcement learning, enabling autonomous agents to adapt dynamically to changing environments or unforeseen disturbances. In robotics, for example, AI-driven controllers optimize motion trajectories, force application, and interaction with uncertain terrain or objects, expanding operational autonomy in manufacturing, exploration, or search and rescue. In manufacturing, AI-powered vision systems inspect components in real time, detecting defects undiscernible to human inspectors. Combined with automated feedback loops, production processes self-correct, minimizing waste and ensuring high quality. Predictive maintenance leverages sensor data feeding AI models that spot early signs of equipment degradation, scheduling interventions to prevent downtime or catastrophic failures. Simulation tools integrate surrogate AI models, accelerating computationally expensive analyses. For instance, fluid dynamics simulations typically require hours or days. Machine learning approximations provide near instantaneous results, facilitating rapid design iterations. However, integrating AI into engineering also presents challenges. Data quality and representativeness critically affect model reliability. Biased or incomplete training datasets can propagate errors or unsafe outcomes. Transparency and interpretability of complex AI models remain non-trivial. Engineers must understand why decisions are made to ensure trust and regulatory compliance. Cybersecurity concerns intensify as AI systems controlling critical infrastructure become potential targets for attacks, manipulating sensor data or control commands. Engineers collaborate with cybersecurity experts to embed robust safeguards and anomaly detection mechanisms. Ethical considerations emerge prominently. Autonomous engineering decisions, such as offline inspection robots or AI-driven design approvals, raise questions about responsibility, accountability, and human oversight. Balancing AI's efficiency with human judgment is vital to prevent unintended consequences. Engineering education adapts accordingly by incorporating AI literacy, data science, and interdisciplinary collaboration skills, alongside foundational disciplines. Hybrid human AI work environments demand new roles, competencies, and workflows, emphasizing complementarity rather than displacement. Applications span aerospace, civil infrastructure, energy grids, biomedical devices, and beyond, amplifying engineering's reach and precision while requiring careful governance, continual validation, and adaptability to evolving capabilities. The confluence of AI and engineering accelerates problem-solving capacity, allowing the tackling of previously intractable challenges through enhanced computation, sensing, and adaptation. Yet it also redefines the engineer's role, emphasizing critical thinking, ethical reflection, and system-level integration as AI increasingly automates detailed, data-heavy tasks. This synergy drives an ongoing revolution, one that expands human potential while demanding rigorous stewardship of powerful new tools. Nanotechnology and biotechnology represent two converging frontiers expanding engineering's reach to life's fundamental scales and mechanisms. These fields challenge traditional design paradigms by manipulating matter at the molecular and cellular levels to create materials and systems with unprecedented functionality. Nanotechnology involves engineering components measured in billionths of a meter. At this scale, quantum effects and surface phenomena dominate, radically altering material properties. Nanomaterials such as carbon nanotubes, graphene sheets, and nanowires exhibit exceptional electrical conductivity, mechanical strength, and chemical reactivity. Engineers harness these traits to fabricate next-generation sensors, transistors, and structural reinforcements far surpassing conventional counterparts in efficiency and performance. Fabrication techniques in nanotechnology demand atomic precision. Methods such as molecular beam epitaxy, atomic layer deposition, and electron beam lithography enable layer-by-layer construction tuned at the atomic or molecular scale. Controlling defects and contaminants becomes paramount, as even single-atom deviations can alter device behavior profoundly. Application areas range from nanoelectronics that power ultra-fast computing to nanomedicine targeting drug delivery with remarkable specificity. Engineers collaborate closely with chemists and physicists to develop multifunctional nanoparticles capable of sensing, imaging, and therapeutic action simultaneously. These particles can traverse biological barriers, delivering payloads directly to diseased cells, minimizing side effects. Biotechnology integrates biological principles with engineering, transforming living systems into tools and products. Tissue engineering combines scaffold design, bioreactor development, and cell biology to grow functional organs and tissues for transplantation or drug testing. Engineers optimize scaffold porosity, mechanical properties, and biodegradability to mimic native extracellular matrices, guiding cell behavior and growth. Synthetic biology rewrites genetic codes to program microorganisms for producing biofuels, pharmaceuticals, or materials. Engineering metabolic pathways involves balancing reaction fluxes, minimizing toxic intermediates, and optimizing yields, challenges addressed through computational models and genetic editing techniques like CRISPR-Cas9. Production scaling requires bioreactor design, maintaining optimal conditions for microbial growth and product formation. Biosensors merge biology and electronics to detect chemical or biological analytes with high sensitivity and selectivity. Applications include environmental monitoring, medical diagnostics, and security. Engineering challenges revolve around immobilizing biorecognition elements, transducing signals reliably, and ensuring device stability under variable conditions. Integration of nanotechnology and biotechnology accelerates development of organ-on-a-chip devices, miniaturized systems, mimicking human organ functions for research and drug screening. Microfabrication, fluid dynamics, and cell culture technologies converge to replicate physiological environments at microscale. Ethical, safety, and regulatory considerations accompany these advances. Manipulating biological systems and designing nanoparticles require comprehensive risk assessment, addressing potential toxicity, ecological impacts, and unforeseen mutations. Engineers engage in transparent communication with stakeholders and policymakers to navigate complex societal implications. Interdisciplinary collaboration defines this arena, merging engineering rigor with biological complexity. Challenges include developing standardized characterization methods, scalable manufacturing processes, and robust quality control for these novel products. These emerging fields hold promise to revolutionize medicine, materials, energy, and environmental remediation by leveraging life's own mechanisms in engineered innovation. Engineering at the nanoscale intertwines with biology, culminating in profound innovations that promise to reshape medicine, material science, and environmental solutions. The convergence of nanotechnology and biotechnology creates a hybrid field where atomic-level manipulation meets living systems complexity, offering precision and functionality previously impossible. At the heart of this union lies the ability to engineer nanoparticles that interact specifically with biological molecules. Unlike bulk materials, nanoparticles exhibit unique surface chemistries and quantum effects, enabling targeted drug delivery systems that transport therapeutic agents directly to disease cells while minimizing collateral damage. This precision enhances treatment efficacy and reduces side effects, transforming cancer therapy, gene editing, and infectious disease management. Fabrication techniques, such as self-assembly, use chemical and biological cues to organize molecules into functional structures spontaneously. Engineers design programmable materials whose components respond to environmental stimuli, pH changes, temperature, or light, activating therapeutic responses on demand. These smart systems blend material science with cellular signaling pathways. Tissue engineering capitalizes on nanoscale topography to influence cell adhesion, differentiation, and growth. Engineered scaffolds mimic extracellular matrices with nanofibrous architectures promoting tissue regeneration, vascularization, and integration upon implantation. Developing these biomimetic frameworks demands precision electrospinning, biocompatible polymers, and advanced imaging to monitor cellular responses. Advances in synthetic biology complement by allowing metabolic pathway reprogramming within cells. Engineered microorganisms produce biofuels, pharmaceuticals, or novel materials sustainably, controlled through gene circuit design akin to electronic logic gates. Scaling these biological factories from lab bench to industrial reactors challenges bioprocess engineering involving fluid dynamics, mass transfer, and system control for optimal yields and stability. Biosensors capitalize on nanoscale transducers, converting biological interactions into measurable electrical or optical signals, with remarkable sensitivity, detecting pathogens, toxins, or biomarkers down to single molecule levels. Microfluidics integrated within these devices manipulate tiny fluid volumes, enabling rapid diagnostics in portable formats essential for personalized medicine and environmental monitoring. Despite remarkable promises, this frontier demands rigorous attention to safety and ethics. Nanoparticles' small size raises concerns about biodistribution, toxicity, and environmental persistence. comprehensive toxicological studies, life cycle assessment, and regulatory frameworks are essential to safeguard human health and ecosystems. The manipulation of genetic material must adhere to strict oversight to prevent unintended consequences or biosecurity threats. Manufacturing processes must achieve repeatability and scalability without sacrificing molecular precision. Engineers develop quality control protocols using spectroscopy, electron microscopy, and real-time monitoring to ensure consistent product performance. Collaborative efforts across disciplines, materials science, molecular biology, chemical engineering, and data science are critical for innovation and translation. The integration of information technology with nanoscale biotechnology spurs development of organ-on-a-chip platforms. These microscale devices simulate human physiological environments, enabling drug testing and disease modeling with unprecedented accuracy and ethical advantage over animal models. Engineers confront multi-physics challenges combining fluid mechanics, cell biology, and sensor integration. Looking ahead, this domain offers transformative potential. Biohybrid robots powered by living muscle tissue, responsive drug delivery systems tuned by real-time feedback, regenerative therapies replacing damaged organs, and materials programmed to self-heal or adapt. These advancements arise from harnessing nature's intricate machinery through engineering rigor. The future of engineering stands at a crossroads where rapid technological convergence, global interconnectedness, and evolving societal expectations shape unprecedented opportunities and complexities. Emerging fields, quantum technologies, advanced materials, augmented reality, autonomous systems intertwine, demanding holistic approaches that transcend traditional disciplinary boundaries. Quantum engineering promises revolutionary advances in computing, sensing, and communications. Harnessing quantum superposition and entanglement, engineers develop devices capable of solving problems impossible for classical computers. Molecular simulations accelerating drug discovery, ultra-secure encryption safeguarding data, and sensors detecting minute magnetic fields with unparalleled precision. Constructing reliable quantum systems requires mastering coherence preservation, error correction, and cryogenic environments, blending physics, material science, and electrical engineering. Simultaneously, the integration of extended reality technologies transforms engineering design, training, and maintenance. Augmented and virtual reality overlay or immerse users in digital environments where engineers visualize complex systems interactively. This enhances spatial understanding, accelerates prototyping, and enables remote collaboration across continents. Development demands optimization of hardware, ergonomics, software latency, and user interface intuitiveness to bridge human cognitive advantages with digital power. Autonomy extends from vehicles to entire manufacturing plants and infrastructure management. Engineering these systems involves real-time data fusion from multi-sensors, machine learning-based decision algorithms, and fail operational safety architectures, ensuring ethical AI behavior, transparency of decision-making, and compliance with regulatory frameworks challenges. Engineers to meld technical rigor with social responsibility. Global collaboration accelerates innovation, but introduces complexity in governance and intellectual property management. Projects spanning multiple nations require harmonizing standards, legal regimes, quality control, and cultural norms. Engineers must navigate geopolitical factors while fostering inclusive environments, valuing diverse perspectives, essential for creative problem solving. Sustainability remains an indispensable compass guiding future engineering. Engineers are tasked with designing regenerative systems that restore ecosystems, achieve carbon neutrality, and ensure equitable resource allocation. Circular economy principles inspire modular, repairable, and recyclable designs, minimizing waste and life cycle environmental impact. Ethical considerations intensify as engineering increasingly influences human identity and freedom. Biotechnologies manipulating genetics, AI systems shaping societal decisions, or pervasive sensing networks demand rigorous ethical frameworks, ensuring privacy, consent, equity, and justice. Engineers bear profound responsibility to integrate ethical foresight throughout design, deployment, and monitoring. Education for future engineers shifts toward cultivating interdisciplinary adaptability, systems thinking, and leadership in complexity. Balancing technical foundation with softer skills prepares practitioners to navigate uncertainty and inspire collaborative innovation. In essence, engineering's future embodies a dynamic interplay of converging technologies, global networks, expanding agency, and ethical stewardship. It calls for visionary engineers empowered not only by knowledge and tools, but by reflexivity and courage to steer humanity toward sustainable prosperity. This final chapter closes the journey through engineering facts with a profound invitation to join the unfolding story where human ingenuity meets responsibility, and the built world evolves continuously with relentless curiosity and care.